Good morning, guys. Alright, I kind of expected this. Everyone kind of burned all their energy, so these are the last one standing. How was the midterm last night? It was reasonable? Wasn't too tough? Yeah, I felt, I don't know, it was interesting to watch you guys write it. It sounds really weird, but I never made exams before. So yesterday I was like, oh, people are trying to answer my questions. And I don't know, I was really enjoying it. And I talked to my roommate about it. I said, I think it's very easy. And then she said, yeah, all the professors think so. So I don't know, I hope you guys think so. So we have come this far. We are actually at week 6. And I think it will be kind of smoothly if we directly transition to chapter 5, because chapter 5 basically focus on trying to write this SQL command based on the relational algebra expression we have learned. However, I would jump all the way to chapter 19 first, because chapter 19 about schema refinement will be the main emphasis on your phase 2 of your project. So what we are teaching today is kind of important, quite important actually. Yeah, and after that, we'll go back to chapter 5. Okay. Let me see. So a few things before we start. I think the midterm should be finished graded next Monday, on Monday. And then we'll talk about it. And then if you have any questions, we can discuss at the time. And also, before we start chapter 19, I want to quickly talk about something that's about chapter 5, because I've been saving this up since the beginning of the semester. There's actually a joke for chapter 5, but I don't want to wait. It's still quite long, and I heard of it at the beginning of the semester. So, as I said before, chapter 5 is writing SQL commands on relational algebra, right? So, as you know, SQL can express relational algebra. So the joke goes like this. One day, SQL walks into the restaurant, and he sees 2 tables, and he asks them, can I join you? Isn't that a great one? Right. I've been waiting for 6 weeks to talk about this, and this is the only audience I've got. So, whatever you guys, this is a reward for coming to class. Okay, let's get started. And I've read a lot more online, but I don't know whether it's my English problem or cultural problem. I just don't get the punchline. I was like reading through up and down, like, so what's so funny about it? But this is the only one I got. Okay, lecture 14, let's get started. The lecture 14 will be on chapter 19. It's about schema refinement and normal forms. So we have talked so much about relational model and designing the database and so on. But how do we know the design we got is the most optimized in different kind of aspects? For example, storage-wise, is it the most optimized, most efficient? So this is what chapter 19 is trying to tell you about. So remember, we were talking about it before. There are bad designs. Some attributes is actually better not to store them. One of the examples will be it's better to not store age, but store the date of birth, because each year the age changes, and it will be easier if we just compute it from date of birth. Another example, for example, when you're designing your online shop, you might store the address with attribute of zip code and also the state, right? However, the state can actually, can directly be derived from the zip code, can it? I assume. So maybe it would be more efficient if we only store in the table the zip code, and then from that we can derive the state. So schema refinement will help you to find this kind of we call functional dependency. So some attributes will depend on the other attribute. Okay? So some problems that might be caused by having redundancy in your database, these are the 4 big categories, or we say 4 types of problems that might be caused. The first one will be redundant storage, as I said before, some information that will be stored repeatedly. So sometimes you don't have to store that much. You just have to have another referencing to that. The second type of problem will be the update anomalies. So here it says if one copy of repeated data is updated, inconsistency might happen. In the sense that if we update the zip code, but for some reason when the administrator manually enter the information and forgot to enter to change the state, then that will cause inconsistency. It would stop following the rules, right? Another one would be insertion anomalies. So it may be possible to store certain information unless, it may be impossible to store information unless some other information is stored as well. For example, when you're typing in, you don't know the state, but you know the zip code. Then what should you do? You should just leave the state as null, or it would be better if some referencing already there. The fourth one will be deletion anomalies. So if we store it just in all one table, sometimes if we delete enough of the entries, we might lose the association, right? Associations of which zip code mapping to which state. So these are the four major types of problems that might be caused by redundancy. So let's talk about functional dependency, as I talked about before. Some attributes will definitely rely on other attributes. So functional dependency, it is actually a type of integrity constraint. So we have learned quite a few different types of integrity constraints before. For example, key constraint is one type, participation constraint is one type. But for key constraint and participation constraint, they can both be presented in the ER diagram. But there are some that cannot be. For example, functional dependency. When we draw the ER diagram, we couldn't observe any attributes relying on other attributes by just looking at your design, right? So some integrity constraints will not show an ER diagram, and functional dependency is one of them. And whenever we talk about functional dependency, the rest of the chapter, we use FD to denote that. A functional dependency occurs when one attribute in a relation uniquely determines another attribute. So this is the example we just talked about, where zip code will determine state. Right. So let's take a look at an example that we will use in this chapter, mostly to talk about FDs, which is the functional dependency. So I guess we just really briefly talked about the hourly employees as one of the entity set in the is-at hierarchy when we were talking about employees entity set, but we never really show an instance of that. So this will be one of it. Let's talk about it. So hourly employees, the schema goes like this. We have SSN, name, parking lot, rating, hourly wages, and hours worked. So here's the instance for that. For the sake of the brevity, in the rest of the chapter, we will just denote the schema in this way. All right, so we would just write the letter. So one letter will represent one field. I quickly circled it, but you don't have to do that. Just so you know, S means SSN, N means name, L means lot, and so on. For now, you might think it's kind of weird, but later on, because we're going to write so many functional dependencies derived from this schema, this will be a lot quicker. Also, because we denote it as this, you might think this means that it has to be in this order. But actually, this is totally equivalent when we write them as just a set, right? So that is because the order doesn't matter. I just want you to remember, the order doesn't matter when we talk about functional dependency. All right. So now you sort of have a sense of what functional dependency might be. Can you observe this table and tell me what sort of dependency you can find from this instance? For example, which attribute definitely rely on another attribute? Observe the values and how they change over rows. Can you find two columns always change together? Yeah.
Well, I know in a lot of places, if you work over 40 hours a week, you get like special overtime pay. So
So then you think the hours worked goes with?
Like hourly wages, because they pay more for overtime.
Yeah, so that would be, we say, from your knowledge of it, right? But from the example, if you look at 40, okay, it maps to 10, 30 maps to 10, but now 30 maps to 7. Anyone else? Yeah.
Rating wages?
Yeah, so if you look at rating and hourly wages, you can see if rating is 8, hourly wages definitely 10, right? If rating is 5, hourly wages definitely 7, and rating is 8, hourly wages definitely 10. Okay, so up here we can kind of assume there are sort of functional dependencies between rating and hourly wages. All right? Sometimes you cannot say this for sure because it might be coincidence. But now, if we think it's reasonable, like your rating, the employee's rating will decide an hourly wages, then we can say there is a functional dependency. So let's see how we would express functional dependencies. So the first one we talked about here. Let's talk about this one first. So the rating, we say it determines hourly wages. Then the way we can write it would be like this. Okay. So you write R, which is the rating, determines with an arrow, and W, which is the hourly wages. You might think based on the instance, you can actually write it the other way around. Okay? But let's just say in this scenario, we think it makes more sense where the rating determines the hourly wages instead of hourly wages determines rating. And another functional dependency you might not notice because it just comes with every table is actually the primary key determines all of the other fields. All right, so here the primary key is SSN and it determines all the other fields. So we write it like this. Okay, so for this kind of functional dependency, naturally it comes with every design of the table because whenever you have the primary key, you should be able to determine all of the other values in other tuples. So this is how we would write down the functional dependency. But if today we want to draw it on the schema, let's take a look at how we would write SSN determines all the other fields. This is how we will actually write it. So starting from SSN, it points to every other field. Okay. So what do you think how we will write the second one? The rating determines hourly wages. We just simply draw one. Short little arrow from rating to hourly wages. So this, what you see right here, is what I want you to do for phase 2. Okay, you want to go back to your design of your ER or of your database, of your schemas, and then identify what are the functional dependencies exist in there, and you want to draw this out. In terms of normalizing them, make them more efficient, or we say optimizing them, we'll talk about it later. Okay. So as we talked about earlier, there are 4 types of problems that might be caused by redundancy, right? So let's take a look at how those 4 types will map to the example we're talking about right here. So the first type of problem we talk about is the redundant storage. So if you take a look at the instance back, we have rating equals to 8 corresponding to hourly wages equal to 3, and we repeat it 3 times. All right? So in some sense, that's not so necessary. We can actually have an external table storing this kind of mapping. And another type of problem, which is the update anomalies, we have hourly wages could be updated without making corresponding change to rating. So that's another potential problem that might be caused by the design. And the third type is insertion anomaly. So we cannot insert a tuple for an employee unless we know the hourly wage for the employee's rating. Okay. So a lot of times if this happens, if the bad design leads to this kind of problem, a lot of times when we enter the tuple, we will have some set to null. Okay. So the fourth type of the problem will be deletion anomalies. If we delete all tuples with the given rating value, we lose the association. So that's like the zip code and state example we talked about. So before we move on, now we know what functional dependency is and what problems it might potentially cause. What kind of solution can you think of? If we take a look at the original table, how would you do to prevent those things from happening? Yeah.
Could you have a separate table that maps rating to hourly wages and just store the ratings here?
So you will want to break this table down into how many? Two. Right. So, yeah, exactly. So what we can do to solve this kind of functional dependencies problem or the redundancy problem is to actually decompose the tables. So that's where we talk about the decomposition. So, problems caused by redundancy can be solved by replacing a relation with the collection of smaller relations. Did I take out the smaller relations? Yes, I. All right, okay, that's good. So it can be replaced with collection of smaller relations. So when you're doing decomposition of a relation schema, let's say the schema, we call it R. Okay, we use uppercase R to denote that. You want to make sure that, all right, you can replace it with two or more. Okay, it doesn't have to be two because sometimes there are more information that you want to do external referencing. And also, you want to make sure the decomposed schemas together, doesn't matter how many you have, 2 or 3, together they have to include all of the attributes in R. Okay? So you cannot be like, I decompose it and just somehow miss some of the columns. Okay, it cannot be that. Let's take a look at how the decomposition will be in action in terms of the example we just looked at. So previously we had this schema, right? Over here, hourly employees with that many attributes, and now we break them down into two smaller tables. So this will be how the final result should look like. Okay? And in some sense, you'll be like, so what's so good about it if you just look at the number of values that's stored? Right now, it doesn't seem like it got less, right? Because here, originally, we have one more column, and that would be 5 cells more, and now we have 4 cells. So that's just 1 cell down. But when your database gets bigger, when your data get more, this will be more efficient. In terms of storage, also, it solved the other problem that we just talked about. So for functional dependency, let's talk about how it will be formally defined. A functional dependency, so as we said before, we will use the arrow to denote that. So x determines y, we use x arrow y. So for x and y, each of them, we say they are a set of attributes. Okay. So it can be multiple attributes for each set. X determines y holds over relation R if for every allowable instance R, small r, little r, of the big R. Okay, it should satisfy this. So here it seems really weird what we are talking about. All right. So for the uppercase R, capital R, it means the whole original schema. Okay, and for small r, it means one of the tuples. Okay, so here we say if for this T1 in R, which means it's a how can we say? Okay, this is the instance, and R, no, this is the schema, and little r is the instance. Okay, so for a tuple in the instance T1, and another tuple T2 in the instance, if we take the X field in T1 and the X field in T2, it implies what if we say X determines Y? Did I make it more confusing? Kind of. It will imply that if you take the Y field from T1, it will also equal to the Y fields in T2. let me talk through it again. So here, R is the relation, so that will be the schema. Okay? And little r will be the instance that satisfies the schema, so that's like the data in the schema. And here T1 is one of the tuples in the instance. T2 is another. Okay. So if we say x determines y, then whenever you take out the x from T1 equal to x from T2, then it should directly imply y from T1 equal to y from T2. Let's take a look at this example right here. If we have an instance of schema ABCD like that, and this is given, if we say A, B together determines C. Okay, let's take a look whether that's true. And we can see whenever we have A1, B1, AB, C will be C1. Whenever A1, B1, C will be C1. And whenever, so these doesn't matter, right? A1, B2, we get C2, A2, B1, we get C1. So we can say that satisfies this functional dependency. Then can we add a tuple that we have A1, B1, C2, D1? Why not? Because that will conflict the functional dependency, right? Because if you take a look, here is A1, B1. According to that, the C should be C1, correct? So the answer is no. We cannot add such a tuple because it violates the functional dependency that is given. So a few more things on functional dependency. We say a functional dependency is a statement about all allowable relations. Okay? So it must be identified based on semantics of application. Like earlier, it was said maybe it will make sense if the hours worked will finally determine the wages, right? So that would be sort of a semantics in the application. So when you're doing your project, you are the one saying which will actually depend on which. Okay. Another thing about functional dependency is that given an allowable instance R1 of relation R, we can check if it violates some of the functional dependencies, like we just did earlier. Right? We saw the instance and we have a tuple. We are checking whether that will violate the functional dependency before we even input. So here, can we tell if F holds over R by checking the instances in database? Remember earlier we were talking about sometimes data that might make you feel like there's some kind of functional dependencies. However, it might be just a coincidence. Right? In different domain, there will be different kind of interpretation. So sometimes it looks like maybe there's a functional dependency there, but it's actually not. It's just because you have so few data points and that they look that way. So we can actually not tell unless it makes sense in your application. Okay. So a few notes on functional dependencies and keys. Let's review a little bit of some of the terms that you might have forgot. So the first one is superkey. Superkey is actually an implicit functional dependency, but it is not minimal, right? Because you might have forgot what superkey is, so here I list the definition of them. Superkey is a set of fields that contains a key, right? And a tuple is always a superkey. Remember that? Superkey. Okay. So why is superkey an implicit functional dependency? Because whenever we have keys, the key can determine all the rest of the fields, right? That's why superkey, because it contains a key. Then the key itself can determine the other fields in superkey. That's why superkey is an implicit functional dependency. But it is not minimal. Why is that? Because like here we said, a tuple is always a superkey. Okay? So it's not minimal because when we say key is actually candidate key, it's not primary key, right? So maybe it doesn't even determine that many, but because they're all inside the key, so the key just determines all the other fields, right? So a function dependency can also determine the candidate key, where we sometimes optionally call it the key. Okay, don't get confused. Candidate key is key. Primary key is primary key. Okay. So let's recall, candidate keys are where no two distinct tuples can have same values in all key fields, and no subset of the set of fields in candidate key is a unique identifier for a tuple. So this means, can candidate keys have primary key as one of the field? No, right? Because then that will be a subset of it. Okay. So here it might get more and more confusing, but let's take a look at how we will actually use functional dependency to find candidate keys. So here I say we have 3 attributes, A, B, and C. If I write here people from that side, can you guys see it over there? Okay. So let's say we have A, B, and C. That's the 3 fields. And for the first case, we have no functional dependency. What do you think the candidate key should be? If no two distinct tuples can have same values, candidate keys. Then what kind of candidate key do you think you can still uniquely identify the tuples? Candidate key is not, right. What do you think?
We just need ABC.
Yeah. So the answer is ABC. Since we have no functional dependency, we use all of them to identify tuples. So right here might still be not so clear, but how about if we say there's a functional dependency where B determines C? What kind of candidate key do you think will be suitable? Yeah.
AB,
Yeah. AB. Why is that?
because if C is determined by B, then there's not really a reason to have C in the key.
Mm-hmm. And we can not only have B, it's because B actually doesn't determine A. Right? So the second one will be AB. Let's take a look at the third one. Including B determines C, we also have AC determines B. This might look kind of weird, but let's do AC determines B. Because this AC determines B. What kind of candidate keys do you think will be in there? There are 2. The first one, the answer is actually A, B, and D. Why is that? The AB comes from B determines C. That's the previous one we talked about. How about AC? If you take a look, AC determines determines B, and then B determines C. By having AC, you determine it all. Right? So that's why we have this. Okay? So that's for this one. Let's take a look at the fourth one, where we also have B determines C. And this time, we have A determines B. What do you think? Which one will be sufficient? Just A, right? Because right here we see A determines B and then B determines C, which means it implies A can actually determine C. So the candidate key right here is just A. We'll talk more about this, like because of which determines which, and then which determines which. There are so many kind of transitions. All right, let's move on. So the reasoning about functional dependencies. Given some functional dependency, we can infer additional functional dependency, like we just did. A determines B, B determines C, so that by that we know A determines C, right? This is what we mean by inferring. So here's an example. If a person's SSN can determine the department ID he works for, and the department ID can determine the parking lot he parks, then what does it imply? The SSN can also determine the lot. Okay? So this is sort of, this is rather intuitive. So this is what we say if the functional dependency F is implied by a set of functional dependencies, which we denote as uppercase F, if F holds whenever all the set of functional dependencies hold. So this is, by this we mean, for example, in the example, this F we can say it's SSN determines a lot, okay? It's implied by a set of functional dependency, which is these two, if it holds whenever all of them hold. Okay. So for this kind of concept, we use F plus in the what's it? Superscript? Superscript. You didn't know that. We call it the closure. F plus we call it the closure of F. It will be set of all the functional dependencies implied. Right? So from a starting point, you might be able to identify some of the functional dependency because of the application, because of your knowledge of your database design. But later on, you might be able to derive all of the other functional dependencies implied by the functional dependency you originally identified. So in the end, if all of them are found, they are called the closure. Okay. So how do we actually find these closure? In today and Friday, we will talk about the Armstrong's axioms that we will actually use. So there are some axioms that we will use to repeatedly apply on the functional dependencies you identify to eventually infer all of the other derived functional dependencies. So now you might be still thinking, what are they? So there are three basic ones right here. So we have reflexivity and augmentation, transitivity. So let's take a look at the first one. So earlier when we talked about that, we say ABC, each of them is a field, but actually you can also think of them as a set of fields, right? Just a set of attributes. So here you can either think of X, Y, Z as just one attribute each, or you can think of them as a set of attributes each. So what reflexivity means is that if Y is a subset of X, then what? What do you think will happen? Who can determine who? Or if you map it to the example, right here, which one do you think is y, which one do you think is x? This is y, this is x, right? Because y is a subset of x. So we say if y is a subset of x, then who determines who?
X can be
X determines y. Okay, so this is rather intuitive, right? If we have, this is really intuitive. If we have this set of attributes of an employee's SSN and the department ID he works for, then we can definitely find his department ID. Okay, this is a very simple one. But because it's so simple, we call them trivial. Okay, which we will talk about more next time. Before we get into the next one, I just want to briefly talk about, so today we'll mainly just focus on why it makes sense, but we won't prove it yet. But on Friday we will prove why they are true. The second one is augmentation. So augmentation, we say if x determines y, okay. Judging by the example, what do you think I would say then? What?
XZ determines YZ.
Yeah, xz determines yz. Okay. So in some sense, this feels like on the left-hand side and right-hand side of an equation, you can multiply by the same values. Okay, it has that kind of sense. So for augmentation, we say if x determines y, then xz determines yz for any z. Here we look at it, we say if an employee's SSN determines his department's ID, then we can imply if together the SSN with the name determines the ID with the name. Okay, that's for augmentation. So far it's still really obvious. Then the third one is actually the one we used already in the example of finding candidate key. That's the transitivity. So we say if x determines y and y determines z, then what? X determines z. Okay. So this is really intuitive as well. If a person's SSN determines his DID and DID determines the lot, that implies SSN determines the lot, which is actually the example in the previous one. Okay, so let's work through each of the axioms and see whether they stay correct. Okay. So for each of them, I will give you the examples of the set of attributes. Let's work on the first one, reflexivity. So say we want to show, this is not proving, even though it looks like proving, we're just showing that it makes sense. So let's show if y is a subset of x, then x determines y using these. It should be really intuitive, right? So for the first thing, you would just want to say if y, so y is a subset of x, then in your example, you say name in the set is a subset of SSN and name both in a set. So these are very simple. I just want you to write down the steps so you can see how they map into examples. So we only have second step left for this one. What do you think the second step will be? In the second line, we want to write therefore x determines y, and then here will be SSN and name determines. Okay, so that's all I want you to write. So judging by this, we can say, if I see that same values for SSN and name, I must also see the same value for name. Okay. the second one? Now you know what to do. What should be the first step? Let's say we want to show if x determines y, then xz determines yz for any z. And the example here we're using is x has only one attribute in the set, is SSN. Y has name, z has parking lot. So what do you think the first step should be? We want to start from the if, right? So x determines y. So that should be, here we say SSN determines name. Then what next? What's the next step?
SSN lot.
Yeah? SSN lot determines name. Okay, that's it. Super simple. So then we can see if I see the same values for SSN in lot, we must also see same value for name in lot. Okay. Then let's get into the third one, which is also really simple. We want to take a look at the example of transitivity. Right. So for transitivity, we want to show if x determines y and y determines z, then x must determine z. And given these examples, I'm sure you can do them, right? You can write them down. First, write down how you will map x determines y. Then write down y determines z. Then the third line is therefore what? Okay, so the first line would just be x determines y, which is SSN determines rating. Okay. Second line would simply be and y determines z, which is rating determines hourly wages. Two of them together will bring you to the therefore x determines z, which is SSN determines hourly wages. So this is the transitivity that we have seen already a few times today. So here I wrote a lot because I want to make sure you know when we read them how it should be interpreted. So we can say if I see that for the same values for SSN, I will see the same value for rating. And if I see the same value for rating, I must have seen the same value for hourly wages. Together, then, if I see SSN, same value for SSN, I will have the same value for hourly wages. Okay, simple as that. So the above three are the Armstrong axioms. Okay, so Armstrong axioms was actually proposed by a guy called Armstrong, and he proposed it, I think, 1974 in a paper on relational model. So he was trying to have the axioms that will help people to identify all of the functional dependencies based on the original sets of functional dependencies. So that brings you to a closure. All right. So there are a couple of theorems for Armstrong axioms. The first one, theorem 1. Armstrong axioms, we can say it is two things, all right? So when we talk about theorems, we can say the axioms are sound, and we can also say it is complete. So Armstrong axiom has both of these properties. It is sound in the sense that the axiom, they can generate only the function dependencies in F plus when applied to a set of F in the functional dependency. Okay? And it's complete in the sense that the repeated application of these rules will generate all of the derived functional dependency in the final closure. Okay? So I won't get into here too much today, but we will prove them on Friday. And these things you can say in other words, they are this, even only if this. Have you guys seen these symbols? So this one, we call it the entails, E-N-T-A-I-Ls, okay? We say uppercase F entails small f, okay? I'll get into more next time, but for now, for this part, this term, the interpretation will be in every model, we talk about the model, this is true, then this must be also true, okay? But for now, just remember this is entails. This is harder to understand, but let's look at here first. For this, if we use this symbol, we're saying it means derive, okay? Or you can say infer. So all of the little f's are derivable from the uppercase F, okay? We say little things on the right-hand side are all derivable from the left-hand side, okay? So for sound and complete together, we will have this, in other words, that's short. So next time, I'm not sure whether I'll prove the completeness, but I'll definitely prove the soundness. And the soundness is a lot easier to do. So the reason we'll be proving them, even though we looked at those axioms and they make sense, but we always want to make it precise and prove why it's correct, right? And other than those three axioms, we actually have some additional rules that we might use really frequently. And they are the union and decomposition. And when I last checked, I found I missed Z on your slide. So it looked really weird if you just read through without the Z. But yeah, put that Z on. So next time I'll also show how you can get the union and decomposition from the three axioms we learned. So now for union, you just have to remember, if X determines Y and X determines Z, then X can together determines YZ, okay? When we put them together, it means taking the union of the sets, all right? And for decomposition, that's the other way around. If we say, if X determines YZ, then separately, X determines Y and X determines Z. Next time, I'll go show how it comes from the axioms. So before we finish the lecture today, let's quickly go through an example. We only have 3 minutes, so I'm not sure whether we can finish them, but we can try. Here's the example schema. So it's the contract schema where we have these attributes. And as we talked about at the beginning of the lecture, we will just use these letters to represent each field. All right? And here I'll give you 3 of the integrity constraints. So let's ignore these sentences first, but just look at here. We have this that comes from the primary key, right? And then we have that, JP together determines Y, and we have SD together determines P. Okay, this is the example we want to use. And let's quickly look at how we can derive more functional dependencies based on these 3. All right? The first one, if we have JP determines C, and C determines that all the other fields, what do you think will happen? By those 2, what can you derive? Yeah, JP determines all the rest, right? Putting them together is very tempting to cancel them out, right? So this determines all of them. It's through which axiom? Transitivity. All right, so through transitivity, we can derive JP determines all the rest of the fields. It's because of transitivity, then the C, we can think of it as the Y. And because earlier we said if a field that can determine all the rest of the tuple is a key, so we can also say JP is a key. So for the second one, where we have SD determines P, here I'll just quickly give you this one. Okay? If we have SD determines P, we can also get SDJ determines JP by adding J on both sides, right? So if you look back to the axioms, This is based on which one?
Augmentation.
Augmentation, right? So it feels like multiplying the same values on both sides of the equation, of the equal sign. Okay, for the third one, what do you think? We have SDJ. Now we derive more, right? So we keep going. Now we derive more. SDJ determines JP, and JP determines this many. So we take the two derived ones together. What more can we write? When you see these together, transitivity, yeah, exactly. So that SDJ determines all the rest. Okay. So now we come to the end of the class. Let's really quickly look at this. Now we have SDJ determines all the rest. Because we talked about multiplication on both sides of the equal sign, isn't it kind of tempting to cancel out both J? No? No? Some people say no. So, we'll talk about why next time. But the answer is no, we cannot do that. Alright? We cannot cancel, even though it might be tempting to do that, but we cannot cancel. So that's for it. I'll see you on Friday. And one last word for the teams. If you, I sent an email last week, right, for the team. So if you want to reform the team, inform me by Thursday. Okay?